Alright, so we're going to get into exponential and logarithmic equations. So a couple things to keep in mind before we begin looking at some examples. We're going to be using the one-to-one property. Remember, that means if the bases of the exponents are the same, then the exponents are the same. So we want to rewrite the equation so that the bases are equal, so we can set the exponents equal and eventually solve for the variable. When we're using natural logs to solve exponential equations, some helpful pointers to keep in mind. We always want to isolate the exponential expression. Then we either want to take the natural log, or we can actually take the common log. It doesn't matter which one we pick, on both sides of the equation. And then we want to simplify by using the properties that we talked about in the previous section. And again, we want to solve for the variables. So start looking at some examples. So let's take a look at this first example. Let's take a look at this first problem. We want to solve for x, and our bases are 64 and 32, and they're raised to some power with a variable in them. I want to rewrite these bases so that they're equivalent. Okay, I know that this I can rewrite it in base 4, but I'm not going to. I'm going to write it with a base of 2. So I know 2 to the 6th power is 6. But it had already a power, so I have to make sure that I rewrite it incorporating both powers. And 32 is 2 to the power of 5, and again incorporate the power that initially had there. So now I have equal bases, and because the bases are equal, now I can say the exponents therefore are equal. So let's go ahead and rewrite that. So 6 times 3x equals 5 times 2 plus x. 6 times 3 is 18x. Distribute that 5, we get 10 plus 5x. I want to subtract 5x on both sides. And we end up with 13x equals 10. Divide by 13 on both sides. X equals 10 over 13. Let's take a look at another example. So this one's a little bit different. Based on the things that we've talked about before, I know that if I introduce the inverse of e, then I can reduce it so that way I end up with just the exponent and figure out what x equals. So what I'm going to do is I'm going to take the natural log of both sides. These are inverses, so now I'm left with x, and x equals ln 4. I'm going to use my calculator to approximate this to 3 place values. And our solution is x is approximately 1.386. If I look at C on our notes, this one's a little bit different because first I need to isolate e to the power of x. Once I do that, then I can take the natural log of both sides. So it just has one additional step. So what I want to do is bring the 19 over, add 19 to 9. Bring the 9 over, add 19 with 9, and we end up with 28. Now I can take the natural log of both sides. These are inverses. X equals ln 28. Now I'm going to use my calculator to approximate it to 3 place values, and x is approximately 3.332. Alright, this one's a little bit different. This time I can't introduce ln and have ln and e reduce and end up with the exponent. This is different in the sense that I can introduce the log, whether it's natural or if it's a common log, and bring the exponent to the front using properties that we talked about in previous sections. So now I can pull the exponent to the front, and it's going to look like this. Negative 2x log 5 equals log 0.15. And now my goal is to isolate x. Well, I know if I divide both sides by negative 2 log 5, I isolate x. And now I just need the help of my calculator to simplify this and approximate x. So x is approximately, whatever I get here, let's put that in our calculator, 0.583. 9, rounding to 3 place values. Be careful when putting this into your calculator. Your calculator does not do order of operations, it just does whatever's next to each other. So recognize that that fraction bar is a grouping symbol, and I need to separate this operation from the top, and then you'll get my solution. Alright, so the next thing I want to talk about is logarithmic functions, and we can solve those a few ways. If possible, I'm going to express the log in an exponential equation. So I want to rewrite it. Solve for the variable, then check proposed solutions. Remember that your solutions have to be in the domain of a logarithm. And for our purposes, our domain are typically from 0 to positive infinity unless some kind of transformation occurred. Other ways to solve for logarithmic functions would be to make sure that the bases are equal, and then you can set what components are equal to each other. So if I have log base b of m equals log base b of, let's say, n, because these bases are equal, so then I can say m equals n. So here are some examples of how we would solve the logarithmic equation algebraically. Let's take a look at this first one. Okay, this one I can rewrite with what I said a moment ago. I want to go ahead and rewrite this as an exponential logarithm. So convert it to an exponential function. Remember, if no base is here, that's a base 10. This is your exponent, this is your output. So that's going to be 10 to the power of 2 equals 5x. 10 to the power of 2 is 100. Divide both sides by 5, x equals 20. And this is within the domain, so we're good. Alright, this one's a little bit different, so what I'm going to do is I'm going to subtract both sides by 5. My goal is to isolate my log as much as possible. So I'm going to subtract 5 from both sides. We end up with 2 ln x equals 9. The next thing I'm going to do is I'm going to pull my exponent back. And then that becomes ln x squared equals 9. And then I'm going to change this, so just like we can take the log of both sides, and if ln and e are next to each other and their inverses, it reduces. Same concept here. I want to introduce something to ln, so that way it simplifies and I'm left with x squared. Well, if I exponentiate both sides, meaning I introduce this as a base and make this an exponent, then I'm able to see that these will in fact reduce. So I want to do it this way. And now I can clearly see this reduces, and I'm left with x squared equals e to the power of 9. What I want to do from here is solve for x. I can take the square root of both sides. X equals plus minus the square root of e to the power of 9. And I just need to make sure that my solution's in the domain. So let's go ahead and put take e to the power of 9, take the square root of that on both sides, and solve. Alright, and we're going to get x is approximately 90.017. Notice that I excluded the negative, because when we plug it back in, that's an extraneous solution, and it's not going to work. We'll get an error in our calculator. It's important to check your solutions. The only one that's going to check is the positive solution. So our solution is approximately 90.017. Okay. Another way to have done this is at this point here, I could have divided both sides by 2. We end up with ln x equals 9 over 2, then exponentiate both sides. This reduces, x equals e to the power of 9 over 2. So you have some options. You're going to end up with this same solution. Alright, for part C, you have to condense before proceeding. So I want to condense based on what we discussed in our previous lesson. And I condensed these two logs because the bases are the same. They're being merged through addition. I can join these with the product. So I'm going to rewrite this as log base 3 x times x minus 2 equals log base 3 of x plus 4. Because the bases are now the same, I can go ahead and equal these components to each other. So we can say distribute the x squared minus 2x is equal to x plus 4. Now I can go ahead and bring everything to one side. X squared minus 3x minus 4 equals 0 and factor. And we're going to get x minus 4 times x plus 1 equals 0. Our solutions are x equals 4, x equals negative 1. When I check these back in the given, this time the negative solution is going to work. So make sure you always plug and check, and let's verbally discuss it. So negative 1 minus negative 2, negative 3 times negative 1, positive 3 works. Negative 1 plus 4, 3, that works. 4 minus 2, 2 times 4, 8. 4 plus 4, 8. So you can see that the solution works. So your solution set's negative 1, positive 4. Alright, so here's our last example. And we want to solve the equation algebraically and round to 3 place values. So when solving this one, I want to go ahead and factor out the e to the power of 2x. And then I'm left with 2x squared plus 2x equals 0. Now I have binomials that I can set equal to 0, and I also have this term by itself. So I have e to the power of 2x equals 0. That's not possible. E to the power of 2 times any number will never equal 0. So this one's not part of our solution, so I can go ahead and exclude that. And now I have 2x squared plus 2x equals 0. Let's go ahead and simplify that. I can factor out a 2x. And then I get x plus 1 equals 0. And I have two solutions from here. I have 2x is equal to 0, and I have x plus 1 equals 0. So here x equals 0, x equals negative 1. Both solutions work in the given, so the solution set to this one is negative 1, 0. I want to go ahead and talk about one more type of problem we might run into in our homework. And let's say I have e to the power of 2x minus 3 e to the power of x plus 2 equals 0. I want you to think about this problem like this. Pretend we had the following. Let's say I had x squared minus 3x plus 2 equals 0. Is that factorable? Yes, it is. X minus 2, x minus 1, and those would be the binomials. So I want you to kind of think about it in the same terms. The only difference is that I have e. So instead of writing x, I'm going to write e, and I'm going to keep the exponent with x. So e to the power of x, because that's where our variable is. And then I have minus 2 e to the power of x minus 1 equals 0. Now I have binomials that I can set equal to 0 and solve. So I have e to the power of x minus 2 equals 0. E to the power of x minus 1 equals 0. Let's go ahead and solve and consider everything we've done in this video. Add 2 to both sides. If I introduce the natural log on both sides, this reduces and I get x equals ln 2. So let's put that in our calculator. Let's round to 2 place values, and we get x is approximately 0.693, and here when I add 1 to both sides, e to this power equals 1. Well, we know anything to the power of 0 must be 1. So here are our solutions for this problem. So whenever you see anything that looks like this, I think it's always easier to think in terms of a trinomial that you can factor and then go ahead and just substitute e to the power of x, because that's where your variable is. Okay? And don't forget to check your solutions in your original.